Good morning, everyone, and welcome to the final day of this year's in-house symposium. And lots of exciting talks are coming your way. And with the speaker Sanjay C P, and he will be talking about waves and tracer dispersion in oceans. Over to you.
Good morning, all. Thanks to the organizers for giving me this opportunity. I'll be talking about waves and tracer dispersion in oceans. This is a work done with Jim Thomas. You might have seen similar pictures in some of the previous talks. So this is some satellite image taken in some part of the ocean, where you can see these are some coherent structures, which are the eddies. They exist in different length scales from like they can vary from order of 1 kilometer to order of 100 kilometers or 1000 kilometers. So these eddies are considered to be the reservoirs for majority of the ocean kinetic energy. And hence many theories have been developed based on this, that the tracer dispersion in oceans is primarily governed by these eddies. However, people have done some in situ observations that they released dyes into the ocean, and they have measured their tracer variance spectra and so on. And according to the theory, it was expected that the tracer variance spectra should go as something like k to the power minus 2, where the theory is based on these mesoscale eddies. But they have observed that in these length scales, especially at these length scales in the range from 10 kilometer to 1 kilometer, which is called the submesoscales in the ocean. So this prediction was deviating from the expected or from theoretical predictions. The observations were deviating from the theoretical predictions. So people have thought that there are some other factors which affect the tracer dispersion in these length scales, and waves could be one of them. So our motivation for this study is this, that we want to see if how waves affect tracer dispersion in ocean. Especially in this particular talk, I will be concentrating on internal waves. So these are the equations. Again, I am not spending much time on these equations. These are Bosniansky equations that can be used to construct different flow regimes having both waves and eddies. And our flow regimes of interest are these three different regimes, where the first one is the quasi-geostrophic regime, where Eg is the energy associated with the eddies and EW is the energy associated with the waves. So in the quasi-geostrophic regime, Eg by EW is very much greater than 1. So in the other way, you can think that quasi-geostrophic regime is a eddy-dominated flow. We also construct another regime, which is called the comparable wave regime, where both the eddies and waves have similar energy, that Eg by EW is almost 1. Another regime, which is called the strong wave regime, we actually, the ratio is fixed to Rossby square. So actually Rossby in our simulations are we are in the low Rossby regime, that we have taken RO is some 0.1 or something. So in this strong wave regime, the wave energy dominates the eddy energy. So you can think that the strong wave regime is as something like a wave dominated flow. So we construct these three different flow regimes and then adduct a tracer field in this. So the tracer is adducted by this equation, simple tracer adduction equation. So I will show you the different flow regime and the corresponding tracer field structures. So what you see on the left-hand side of the top row, this is just the vorticity. I'm plotting the vorticity in this 3D domain. So you can see in the QG regime where eddies are dominated, you can see large-scale structures, large coherent structures. And correspondingly, in the tracer field structures, you can see the tracers get trapped or like they are not mixed well in this quasi-geostrophic regime. However, if you go to the comparable wave regime, you can see that there are coherent structures, some coherent vortex structures are there, but however, you can also see some small scale structures here because of the presence of waves. And if you look at the tracer field structure, you can see it gets mixed well in this comparable wave regime compared to the QG regime. We have one more regime, which is the strong wave regime. Here I am plotting horizontal divergence because that is the dominant flow field in the case of a wave dominated flow. And you can again see that in strong wave regime also the tracer field gets mixed well. So it's actually in the steady state I am showing the video. So in the initialization, I am initializing the tracer field on the large scale in the domain. Now to get some quantifications, we first calculate the tracer variance spectra, which is actually tells us the distribution of tracer variance along the for different wave numbers. So in QG regime, you can see the tracer variance content in all the wave numbers is very high compared to comparable wave and strong wave regime. They are showing a steeper spectra, which tells us that stirring and mixing is in a way is more good in comparable wave and strong wave regime. We also calculate the flux, the tracer variance flux, which is basically the amount of tracer variance is transferred from the large scale to the small scales. Again, you can see in strong wave and comparable wave regime, the tracer variance flux is very high compared to the QG regime, which is like almost 20 times more in this comparable wave and strong wave regime. However, till this point, it is not sure whether waves are doing the things. So we further split the flux into into the contribution from the eddies and the contribution from the waves. So in QG regime, you can see the total flux is dominated by or it's overlapped by the contribution from the eddies, which is expected because there are no waves in this QG regime. However, in comparable wave regime, you can see that there is enough contribution from the wave part, and in the strong wave regime, the total flux is actually dominated by the wave part. Now we have introduced waves, but we are not sure because we are evolving a nonlinear equations. We are not sure whether we have linear waves here. So we look at this dispersion relation and see if this is our flow field satisfies these equations. So for this, we plot the velocity field. Actually, this is for the comparable wave regime I am showing. We plot the velocity field in the omega kh plane, and we see that these white lines are the dispersion relation, which is for this specific kz equal to 20. You can see a bright region along this line, which tells us that in our system we have linear waves because it follows the dispersion relation. Still, I mean, there are some spread. It's not, we cannot completely say that it's fully nonlinear, but we have linear waves. We have looked at it for different values of kz, and in all these cases, we can see this dispersion relation is satisfied. So we also wanted to look at the physical regions in the physical space where this tracer flux is maximum, or like where this tracer flux is accommodated. To do that, we use a filter. This is some kind of, you can think of like we are going to a large scale tracer values. We use this filtering, apply this to the full tracer equation, and then obtain an equation for the large scale tracer variance, which is basically tracer square. And then the right hand side term is the flux. So I am just showing this pi obtained in the QG regime. So if I plot this in the 3D domain, you will get a structure like this, and you can still see, like, because it's in the QG regime, the large scale coherent structures are still visible in the flux. So now we wanted to see where this like maximum tracer flux is located in the physical region. To do that, we first find a cumulative sum or cumulative distribution where we made this flux as a function of the vorticity, the normalized vorticity values. And this is what we obtained for the QG regime. So what I'm plotting is the cumulative distribution on the y-axis, and the x-axis is the theta g by the vorticity, normalized vorticity. So you can see that there is a sharp increase to the value 1, meaning that 90% of the flux is located below these values, below 12% of the maximum value of the vorticity. So this is for the QG case. Similar observation we see in comparable wave case and the strong wave case. So despite this difference in the flow regimes, in all these cases we see that 90% of the flux is located in small values of the flow field. Now we look at that these regions, what are these regions in the physical space? So this is just the 3D snapshots of the full vorticity field in QG, comparable wave and strong wave. Now we plot only those regions which have 90% of the tracer flux in QG, comparable wave and strong wave. So you can see the coherent vortex structures are excluded, meaning that 90% of the flux in both comparable wave and QG are located outside the coherent structures, outside the coherent vortices. Similarly, in strong wave, they are it's not that clear, but it's actually the high divergence values are been zeroed out. So we also looked at the tracer variance, where this 90% of the tracer variance is located. It is also showing similar behavior. So this is the summary of my talk. So we have looked at how internal waves affect tracer dispersion, and we see that wave-rich flows almost 20 times more efficient than eddy-rich flows. Despite the difference in flow regimes, we found that 90% of the tracer flux is located in regions of weak flow fields. This work actually tells us that the role of waves has to be taken into consideration in large-scale global ocean circulation models. Thank you.
We are ready for questions.
I didn't understand actually, because in the experiments you said it will go like 1 by k cube, and where you were able to explain that.
Not actually. So what? So in experiments, even though what they actually observed is that there is some deviation from the theoretical predictions, but they also couldn't tell like why you are seeing such a power law. So here also we see some deviation from -2, which is which is the theoretical predictions, but we don't have any theory or something which to say that like in these scales it should go as like this. So there is no universal power law or something. It can deviate from the predictions. That's.
Any more questions? All right. If not, then let's thank Sanjay again.